तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will continue our discussion on partial differential equations, that is differential equations of the form given here, that is A del squared u by del x square plus B del square u by del x del y plus C del square u by del x del y square plus f of a function of u x y del u by del x and del u by del y equal to 0. So this is a general form of partial differential equations which we will be looking at, where variables, this function is the second derivatives here are linear in u. So that is the kind of functions we will be looking at. In fact, we will be specific examples we will be looking at will be only equations that are linear in u, okay, and for different values of a, b and c and f. So with this we saw that in the last class that with this general form for the partial differential equations, where u is a function of both x and y, we can classify this into three different categories, that is depending upon these coefficients, what the value of these coefficients are. That is, if b is 0 and when a and c are positive, and then we call that as elliptic partial differential equations, that is of this form, that is b squared minus 4ac less than 0. So if b is 0, then for a and c are positive, then you have elliptic partial differential equation, an example being the Laplace equation. One equation which we will be looking at. And then we could have parabolic equations where b squared minus 4ac is 0. So that could happen if both b and one of these coefficients a or c are 0. Okay, that is the case which you would be looking at here in the case of a diffusion equation or a heat equation in one dimensions. So that is the case where you have a parabolic equation. See that there is only one, the second derivative is only a function of, second derivative is only in x on one space dimension, space variable, and then u is a function of time too in this particular example. Okay, that is a heat equation. Okay. Or you could have cases where b squared minus 4ac is greater than 0, that is, that kind of equations are hyperbolic equations, and for example being that of a wave equation. So in this case now here you have again b is 0, but a and c are opposite signs. So now we are taking one variable as x and other variable as time in this particular example. So that is a solution, that is an example of hyperbolic equation, that is a wave equation in one dimension. So we have elliptic equations and we have parabolic equations, and then we have hyperbolic equations. Okay, so we look at more specific case of Laplace's equation, which arises quite often in science and engineering. For example, when you want to deal with the case of the heat flow, the steady state solution of this particular thing, there is a slab here, okay, and let us say slab has a thickness, let us say delta z, okay, and then now you cover the slab, you insulate the slab on the top and the bottom, and then you let the heat flow only through the sides. In this example, there is heat coming in from this side and this side, and then going out through this and this side. So that is, we keep this at these two sides at a higher temperature with respect to these two sides. and then you could ask the question, what is the steady state solution of this, of the temperatures? That is, you want to know what is the temperature profile in this slab, okay, as at steady state, that is when this temperature is not changing with respect to time. So to begin with, it will change with time. So to start with, let us say you keep it at some 100 degrees on this side and 0 degrees on this side, and then there is a flow of heat, and so as we start with, there will be change of temperature in this region, and then after some time it reaches a steady state, and you want to know what are the steady state temperature distributions in this area is. So then what would you do? We would write that, we will say Qx is the heat flow in that direction and Qy is the heat flow in this direction. So that is the amount of heat per unit area per unit time which is flowing out in this region in this direction, and Qx is the amount of heat which is flowing out in this region, in this direction per unit area per unit time. So then you take a small section like this, and then you say that whatever coming in should go out at steady state, because the temperature here is not changing. Okay, so whatever heat which comes in should go out, and we have insulated the top and bottom of the slab, so the flow is only in the xy plane. So that simplifies our analysis here. And then you say what's the heat which comes in. The what comes in should be, so we are looking at something like this. So we are looking at a small section, right, and then we are saying that what comes in here is Qx, okay, and then comes here is Qy, Qy, and what goes out here, now things go out here. Okay, so now this thickness is delta x and delta y, so what goes out here is Qx plus delta x, and what goes out here is Qy plus delta y. So what is the total heat coming in here should be Qx, Q at x, that is the heat flow, that is per unit area per unit time. So this is a delta xy plane, right. So this is the x direction, that is a y direction, and z is the thickness of the sample. So we have delta y into delta z as the cross section of this plane coming in, and in time delta t. So that will be the heat coming in time delta t in through this, and similarly what is the heat coming in here, but that will be Qy into delta x and delta z delta t. So that is the net heat which is coming in, and at steady state this should be equal to what is going out. So that should, what is going out is the following, that is Q of x plus delta x, sorry, this is y plus delta y, this is y plus delta y, and this is x plus delta x. That is our x direction and this is our y direction. So Qx plus delta x into delta y delta z delta t, that is a heat going out there, and the heat going out here, sorry, heat going out here and the heat going out there would be Q y plus delta y into delta x delta z delta t. So that will be the heat which is going out. So this equation, so we equate these two, right, and then we can rearrange the terms and then write it as Qx minus Qx plus delta x into delta x delta, so delta z can delta t cancels everywhere, so we can write this as Q into x plus delta x minus Qx into delta y plus Qy plus delta y minus Qy into delta x equal to 0. Right, so I just rearrange the terms and I can write that. Okay. And from this, so I can write this, then from here I can write this as Qx plus delta x minus Qy, dividing the whole thing by delta x into delta y. I can write this as Qx plus delta x minus Qx divided by delta x plus Qy plus delta y minus Qy divided by delta y equal to 0. So now remember, this is the definition of the forward difference for the first derivative. Okay, so when you replace the first derivative by the forward difference method. This is the definition of the forward difference. So you can write this as del q by del x, and then that's del q by del y equal to 0. That's what we get here. Well, remember, q is the heat flux, that is the quantity of heat which flows in per unit area per unit time. So that's what the q is. So now in this case, because now what we remember what we are looking at is an example of an elliptic partial differential equation. So this is one case where that arises. So now we have written this equation for the heat flow in terms of the problem of the heat flow on a slab in the xy plane in terms of the currents, the heat currents. Okay, now we want to write this in terms of the temperature. Okay, so what we have done so far is to just say that what is the net heat coming in, that is qx into delta y into delta z into delta t, that is basically this heat current multiplied by this cross sectional area here multiplied by time, and similarly whatever coming in here, this qy, the current, multiplied by the cross sectional area multiplied by time, that's a flux multiplied by the area multiplied by the time. So that's, we are equating this to what's going out. So then we have this equation, and from this equation we could write this as del q by del x plus del q by del y equal to 0. That's a equation which we got. But now the q's are the fluxes, and then these fluxes are related to the temperature by the Fourier's law, right, which also we know that is saying that q is proportional to this q. So we are saying we connect this fluxes by the Fourier's law to the temperature. So now this is we denote the flux in the x direction by qx here, and the flux in the y direction by qy. So we are saying the fluxes are related to the temperature gradient through the Fourier's law, which tells us that qx, the flux in the x direction, is proportional to the gradient in temperature. We call u as the temperature here, and gradient in the temperature in the x direction. Okay, so we use u for temperature to distinguish it from t, which is time. Okay, so this, now we substitute this here. Okay, so that is q is equal to a constant times the gradient in that direction. We substitute here, then that will give us del squared u by del x squared plus del squared u by del y squared equal to 0. So that's the Laplace's equation which you are looking for. Okay, so now this is one case where we obtain the Laplace's equation. That is the case where we want to know what is the steady state temperature distribution of a slab when the heat comes in through the sides and goes out through the side. That is, the top and the bottom is insulated, and then you have the two-dimensional flow of heat, and then the steady state will be given by the steady state distribution of temperature u. The u is the temperature here, is given by the Laplace's equation. So we look at this as a specific example for elliptic partial differential equation, and then see how we can solve this equation using replacing the derivatives by its difference equations. So that's what we will be looking at now. So let me summarize this. So we have the Fourier's law, which says that the flux in the x direction, or any direction I, is related to the gradient of temperature, right, in that direction, and multiplied by some constants. Over here it's k is the coefficient of thermal diffusivity, rho is the density, and c is the heat capacity. And that would lead, when you substitute that here, leads to the Laplace's equation. So now in the case where there is a source, this equation would be Poisson's equation. That's also another example. So we could have, for example, a particular source sitting there. Okay, now that's kept at a constant temperature. So if you have the slab where the middle of the slab or some part of the slab is kept at a constant temperature, so that's like having a source in that point. And then you have this equation here. On the right hand side of that would be a source term, so that will give us the Laplace's equation. So both equations can be solved by similar methods, that is basically replacing this derivatives, this second derivatives, by the difference equations. So now remember what the difference equations were. Okay, so when you said that the first derivative, as you can see here, the first derivative comes from this, or when you want to do a first derivative, you can replace this by a difference equation. Now similarly, you can replace the second derivative also by a difference equation. So we will write that now. So when you want to write equation of this type, so del squared u by del x squared equal to del x squared. Okay, so let's say we will replace this particular term, so that what you do is we can write it as u x plus delta x minus 2ux plus u x minus delta x divided by delta x squared. So that is something which we can that's one thing which we can use, one scheme in which one scheme or one way of replacing this derivative by its difference equation. Okay, now this is a symmetric difference equation for the second derivative. Okay, so similarly you can write for y also and replace it in our Laplace's equation. So our Laplace's equation, which was del squared u by del x squared plus del squared u by del y squared, will now become u x plus delta x minus 2 ux plus u x minus delta x divided by delta x squared plus u y plus delta y minus 2 uy okay, so the uy plus uy minus delta y divided by delta y squared. So this term is evaluated at a constant y value, while this is evaluated at a constant x value. Okay, so that's the way we do it. So we can actually, when we write this, we should actually write it as x. So we should write this as comma y minus 2u x comma y, that's evaluated at the constant y value, plus u x minus delta x comma y. Similarly here we should write this as u x y plus delta y minus 2 u x y plus u times x comma y minus delta y. So that's the equation which we will write. Okay, so we have these two equations replacing these. We have this equation this terms replacing these two terms, okay, in this equation. Okay, so now we can write this whole thing as u x plus delta x comma y plus u x minus delta x comma y plus u divided by, okay, so now in the special case, okay, in the special case where delta x equal to delta y, we can simplify this equation and write it in this form. Okay, so in this special case we can write this as u x y plus delta y comma plus u x y minus delta y. So plus 4 minus 4 u x comma y, right? So whole thing divided by delta x squared. Okay, so this equation in the special case where delta x and delta y are the same, that is, we are going to replace all this derivatives by its difference equation. So that means we are going to discretize space and write this in a grid, so that we have discretized space now. That is, x goes up by delta x and y goes up by delta y from point to point. So then, and let's say we discretize x and y directions by the same amount, that is delta x and delta y. So by this what I mean is that you take a piece like this, right, and you want to know now, for example, the heat distribution, the temperature distribution inside this. Then what we do is we actually make a grid here, right? And and then we try to write the equations for every point on this grid. Okay, so we write this grid and we write equations for every point on this grid. So now if this spacing and this spacing are the same, we take a square grid and we take this spacing and this spacing to be the same, and then we can simplify this equation to if you use this, we can simplify this equation to this form. So now what's the advantage of doing this is that now we know that every point is separated by equal distance, and then I can replace all this by an index, okay, both x and points by an index, and write this in a much more simple form. So this is the basic idea. So that as we replace this equation by its difference equation, now this equal to 0 is the equation which we have to solve. Okay. So now let me summarize that once again here. So we have the equation, so with the second derivative in that direction. Now notice that I have replaced them by indices. Okay, so indices in this case, and again that is I is my x index and j is my y index. Okay, so I'm going to say that each point is now represented by an ij. Okay, so each point on this vertex is now I, comma j. Okay, so I goes up in that direction and j goes up in this direction. So that's what this is. Okay, and then you have the equation as x minus delta x is now I minus 1, and x plus delta x is I plus 1, okay, and x y is ij. And then I can write this equation in this form, that ui minus 1j minus 2 uij plus ui plus 1j and by delta x square, and then uij minus 1 minus 2 uij plus uij plus 1 by delta y square equal to 0 as my Laplace's equation now. So then this equation now is valid for every point on this lattice, right? So when I write this equation now in the index form, okay, and then that is valid at every point on this lattice. Okay. So I have to solve that equation. So if I have an n by n lattices here, so n by n grid, okay, then I have n into n equations to solve, okay, in this particular case. Okay, so every point I and j I have an equation. So you will have n into n equations to solve to get this solution. Okay, so we will write that down specifically. So we choose this particular simplification, that is delta x is equal to delta y, okay, and to write this in a much more simple form which we just now saw. Okay, and then you can write the equations now as in the index form as u I j, so ui plus 1 comma j plus ui minus 1 comma j plus ui comma j plus 1 plus ui comma j minus 1. Okay, so repeat this, ui plus 1j, ui minus 1j, so that's x plus delta x minus delta x, and y plus delta x, or delta y and y minus delta y, and that's equal minus 4 times uij equal to 0. Okay, that's our equation. That's the equation which we have to solve. And now this for every I, so I going from 1 to n and j going from 1 to n. Okay, we have to solve that. So now this is a differential equation which we have to solve. So we obviously need boundary conditions for this. Okay, and so we can see that very clearly when you write this, as I said, for every I and j values. Okay, so now if I try to write that this equation for a point on the boundary here, okay, and then I will have trouble, because on the boundary then I will have to say, for example, if I take this boundary and then I have to specify this is j equal to n, let's say. Now I have to specify j plus 1, so that is because I need j plus 1 here. Okay, so if I specify it on the boundary, the j plus 1 is not known, so I cannot do that. So I cannot write this equation on the boundary. So you can see the need for boundary conditions to solve this equation. So how do we put in the boundary conditions? So that's also we'll see now. So let's take a small grid and then write this down explicitly. So we have a let us say we have a grid like this here. So we make a grid of this form. So we have j, so the I value going in this direction and j value going in that direction. Let us say, so this is 0 comma 0, and then similarly we have 1. Okay, so we have a grid like this, and then we put on this grid the points, that is, this is 0 comma 0, so this is 0, 1, 2, 3, 4, and this is 0, this is 1, 2, 3, 4. Okay, so we have a grid, some grid like that. Okay, and now we want to solve equations for every point on this grid. So if I want to write the equation here, right, so then that is now 2 comma 2, so this point is 2 comma 2, right, so that's what this point is. So I want to write this equation here, I would write it as u 3 comma 2 plus u 1 comma 2 plus u 2 comma 3 plus u 2 comma 1 minus 4 u 2 comma 2 equal to 0. So that's the equation I would write for this point. And now if I want to write for, let's say, this point, that is now 2 comma 0. Okay. Now if I want to write for this point, I can see that I will have, so this is for 2 comma 2. Now for 2 comma 0, that is I is 0, I is 2, j is 0, and then I have to write it as 3 comma 0 plus u, I will have 1 comma 2 plus u 2 comma 3, 2 comma 1, j is 0, plus u 2 comma minus 1 plus minus 4 u 2 comma 0 equal to 0. Okay, so now we can see that this point we don't know what it is. Okay, so obviously we cannot write equations on the boundary nodes as easily as the interior nodes. Okay, so this scheme differentiates the boundary nodes and the interior nodes. So something has to be done to actually specify the points there. Okay, now there are two ways of doing this. Okay, now these points are specified by the boundary conditions. Okay, so if you want to write this equations at the boundary, okay, and then you need special conditions. Okay. So there are two ways of doing this. One is that we don't write the equations at the boundary because the boundary conditions specify what is the value of u at the boundary is. Okay, so in our example of temperature distribution, it is specified what is the temperature at this boundary nodes are. That's one case. Another case is that we don't know what the temperature that there is, but we know what the derivative of the temperature at that boundary are. So there are two specific examples which we should be looking at. So let's look at the first example where we have the boundary conditions specified in terms of the temperature there. Okay, so we are given the temperature at these boundary points. Okay, so that is, so now we look at the example. So let's say we have kept this at 75 degrees here, and then this is at 50 degrees, and we say this is kept at 100 degrees and this is kept at 0 degrees. So that is u equal to 50, u equal to 100, u equal to 75, and u equal to 0. Okay, so now that's the starting condition, that's a condition which we have given. Okay, so we maintain this four boundaries at okay, so we maintain these four boundaries at the specific temperatures given. Okay, and then we want to find out what's the temperature distribution inside is at steady state. Okay, that is, solve this equation with this boundary condition. Okay, so now obviously I don't have to write this because I know that the solution for 0 is now that u 2 comma 0 is 75. I know that. I guess I don't need to write that equation. Okay. So I need to write only for these 9 points, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, the boundary conditions are specified. Okay, so these corner points we either denote with this boundary or with that boundary. So that's a condition which we can look at. Okay, So then we can write down the whole equations for all the boundary points. Okay, so we can do that here. For example, if I want to write it for this case, okay, so that is, so let's write it for some points. So we'll write it for this particular point as 1 1. Okay, so we'll write it as, so for the case 1 comma 1, okay, I would write that as u2 comma 1 plus u0 comma 1 and plus u1 comma 2 plus u1 comma 0 minus 4u1 1 equal to 0. And now then I will write for the next point, that is for 1 comma 2 comma 1. Okay, so when I write for 2 comma 1, I will have u 3 comma 1 plus u1 comma 1 plus u. So we are writing this now for 2 comma 1. So then we have u 2 comma 2 plus u 2 comma 0 minus 4u 2 comma 1. Okay, that's equal to 0. So we get 9 equations like this, and you can see that they are all coupled. So that is u11 appears here, u11 appears here. So that you get 9 simultaneous equations like this, and we know how to solve such simultaneous equations. Okay, so we know how to solve simultaneous equations, linear equations. Okay, as I said, we will deal only with linear equations, partial differential equations which are linear in the variable u, so that we can write them as using the difference scheme as linear simultaneous equations, and we know how to solve those equations using matrix methods. Okay, we can look at an example of such a case in this. So now let me just summarize before that. Okay, so what I am trying to do is here is to write into the particular case where delta x and delta y are the same. Okay, and write this these equations. This equations. Okay, in the form that ui plus 1 ui minus 1j minus ui plus 1j plus, so ui minus 1j plus ui plus 1j plus uij minus 1 and plus uij plus 1 minus 4 uij equal to 0 when delta x and delta y are the same. That's what we are doing in this particular case. Okay, so now let's look at a specific example where we implement this simple boundary condition, that is this fixed temperature at the boundaries, right? And then we solve 9 such equations linearly. So it's obvious to us that we can actually solve these equations by the matrix methods we know, right? So we have these 9 equations, and we can just invert this matrix by using the matrix methods. As for example, in this case again, we know what these values of u01 and u10 are. Okay, so for example, because these boundaries are fixed, right? So u01 is all fixed at u01, u02, u03, u04, etc. are fixed at 100. So this simply, this value is replaced by 100. Okay, and similarly u10. So that is when the x is 1 and this u is 0. So u10, u20, u30, u40 are fixed at 75. So I can replace this by that number. So boundary conditions enter through this in these equations through these variables at these points. So finally when we write this equation, so for example here you will get it as u21 plus u12 minus 4u11 equal to minus u01 minus u10. Okay, so minus u01 is 100, so minus 100 minus u10, so u10 is 75. Okay, so that's what you would get. So this is minus 175. So minus left hand side is minus 175. So all other terms, okay, are 0 in this, right? Okay, and similarly here you will have u31 plus u11 plus u22 plus minus 4u21 is equal to minus u20. So u20 is again minus 75, so it is minus 75. Okay. With the unknowns, we can write them in a column matrix form. So we can write that in a column matrix. So then we will write it as U11, U21, etc., and then U12, U22, etc. Okay. So we will have 9 such elements corresponding to temperatures at 9 points. Okay. And then we can write this as a matrix form. But most of the elements in that matrix would be 0, as you can see. Okay. Most of the elements here would be 0, because the first, if I want to write the first column here, okay, the first equation, you can see the U11 is 0, so it is 0, and then I can write it as 0 plus 1 plus, so I have U11, U21 is 1, and then you have U31, and U31 is 0, so that is 0, and then you have U41. So I have U11 and U21 and U31. So I have to write that, so that U21, U31, and then I have U12, okay, U12 is 1, okay, U22 is 0, and then I have U23, which is 0, right. So I keep going this way. Okay. So I have lots of terms which are 0 in this equation. Okay, U11 is not 0, that is minus 4. Okay. So I can write this equation. When I write this equation using all these variables, okay, I get lots of zeros there. Okay. And then, so in my matrix equation, we'll have most of the elements as 0. Okay. So such matrices are known as sparse matrices. Okay. So using a inversion scheme, okay, to solve such matrices, matrix equations, where most of the elements are 0, is not very advantageous. Okay. So let me summarize this once again by writing it like here. Okay. So what I want to do is to write, what we'll be doing is, when we write the equations, when we write this the differential equation in the difference equation form, okay, we would be writing things of this type, right. So we will write equations of this type, okay, one for every point on this lattice, okay, we will keep writing equations of this form. Okay. Now these equations I can write in the following form, that is, I can write it as let's say A11 U11 plus A12 U12 plus I used 2 1 here, okay, plus A13 U13, etc., okay, equal to 0, or equal to some function we may call f1, okay, and similarly A21 U21 plus A22 U22. Okay, so I can write it in a matrix form where U11, U12, U13 are our unknowns, and A11, A12, A13 are our coefficients. So if I compare this equation here, okay, with the equation which we have here, okay, and then I can see that most of those coefficients are simply zeros. Okay, right. So that's the point which I was trying to make. Okay, so I have this equation which is now written as A11 U11, A12 U12, A13 U13, etc. So that I can finally write this equation as A11, A12, A13, A21, A22, A23 in this form as a matrix, okay, multiplied by U11, U12, U13, U21, U2, etc. I can write it in this form as some right hand side which is given by F1, F2, F3, etc. So I can write it in this form. That is what we normally do when I have a set of simultaneous linear equations to solve. But the point here is that most of these variables, most of these coefficients here are 0. Okay, so what we get this matrix here would be that most of the elements of this matrix would be 0. So this will be what's called a sparse matrix. So for that kind of matrices, okay, when you have large number of such equations, that is, we have a grid which is very large, okay, inverting this matrix to solve this equation is not numerically efficient. Okay. So that's a point which I want to make. So it looks like it's clear that I can replace my partial differential equation by a difference equation and write the solution, write the equation in this kind of a matrix form, okay, by discretizing space. Okay, I can write it in a matrix form. Okay, however, most of these elements will be 0, and hence this matrix would be what's called a sparse matrix, and inverting such a matrix to solve this kind of equation are not numerically efficient. Okay, it turns out a better way of doing this would be simply use an iterative scheme. Okay, that is to say that we had this equation that ui plus 1j plus ui minus 1j plus uij plus 1 plus uij minus 1 minus 4uij equal to 0. So that's what the equation we had. That is where it is from here that we have written all this forms, right? Okay, so now this equation I can write as uij equal to ui plus 1j plus ui minus 1j plus uij plus 1 plus uij minus 1 divided by 4, right? So I can write this equation in this form. Okay, so then what I do is I start with the uij values. Let's say in this particular example, what I do is I know the boundary conditions, okay, and I put everywhere else it as 0. Okay, and then I iterate it. Okay, I obtain what uij's are. By using this equation, I'll get the new uij values for all the interior points. Okay, and then I put them back again into this equation and iterate it back till I get a steady state solution. Till this term gives me a value which doesn't change. Okay, that is, so let me repeat this. So instead of solving a sparse matrix like this, okay, the method which is normally used for solving elliptic partial differential equations is the following: that you write the equation in this form. That is, you write this equation, this, for example, in the case, not all elliptic partial differential equations, in the case of Laplace's equation, you can write the equation in this form as a difference equation, and then you say that I use this equation to compute uij values from my guess values of ui plus 1, ui minus 1, j plus 1 and j minus 1 values. Okay. This particular example, what we do is we know the boundary conditions. Okay, so we know that that my grid on my grid this boundary points are fixed at with different u values. Okay, and then I can write and then I start with the interior points are all given some temperature. Let's say I give it a 0, okay, and then I evolve it, okay, in this using this equations. Okay, and after some time, so I will see that the values inside would keep changing at every iterative loop. Okay, and finally it will come to a point where the temperatures don't change anymore, right? And then I say that I have reached a steady state. So that's the kind of equation which we will look at now. So we look at one example of this now. So here is a program which does this thing. Okay, so I have fixed my boundary conditions. So let's see what we have fixed my boundary conditions as 75, 50, 100 and 0. Okay, so that's similar to what we have just fixed it here. Okay, so I have given, as we can see, the boundary points. Okay, that is I, so all values of I going from 0 to n. Okay, the one boundary point 0 is given as 75, and other one that is at n is for all I values at n it's given as 50, and all I values at 0i is 100, and all I values ni is 0. Okay, and I stored the same thing in another matrix called S for reasons which I'll tell you just now, okay, in a minute. Okay, so this is the boundary condition specified. Okay, and so now I have this matrix, okay, matrix which is n by n matrix, okay, n plus 1 by n plus 1 matrix. And then what I do is I use this equation. It's a very simple program. So this I just use this equation. Okay, I have used this equation that my new value of ij is the sum of I plus 1j, I minus 1j, ij minus 1 and ij plus 1 divided by 4. Okay, so it is just this equation. I just use this equation. I used a new matrix here S. Okay. So I start with all some values given to u, okay, and evaluate the new values of uij, and which in my program I call S, okay, and then I will see whether the S and u are the same or not. If you have reached a steady state, then the S and the u would be the same. Okay, that is the values I started with and the new values I got should be the same. Okay, and if it's not the same, I go back and then do the iteration again. Okay, so I start with all this. Here it is D. Okay, all the matrix elements are called D. Okay, and from the D matrix I compute the new S values. Okay, and I compare. I am just finding out what is the difference between the D and S are. Okay, for all points I and j. Okay, that's my total error. Okay, now if this error is less than 10 power of minus 2 here, I stop the iteration. So I continue the iteration till this becomes less than 10 power of minus 2. Right, that's what this program is. So after one iteration loop is over, I transfer all D values to S values. Okay, and then all S values to new D values. Okay, and then go back and do the iteration again. Okay, till my D and S are the same. Okay. So that's what the program is. So we just run this program and see. Okay, so now that's what I did was I started with this. So you can see the top points are all 100. Okay, and this side is 75, bottom is 0, and this side is 50. That's what my boundary condition is. Okay, and I had started with every point as 0 in the interior point as 0. So now this is after one iteration. Okay, so I started with all interior points as 0, as you can see in the program. I'll show you that again. So all interior points I give as 0. So all points are given 0, okay, except the boundary points. So that's what I started with. Okay, and then after one iteration, I goes into the interior points are changed. Okay, now they are not 0 anymore; they changed. And then I go to the next iteration loop, and you can see the interior points are changing further. Okay, and these boundary points are held fixed. Okay, and then we keep doing this iteration. Okay, and you can see that the values are changing. So the values change, and then finally it would reach a steady value. Okay. So then after that it doesn't change anymore. Now you can see that it doesn't change very much. Okay, so it has reached kind of a steady value. Okay. So when it reaches a steady value, this program should come out. Okay. So that's what I'm trying to do. Okay, so it runs for many loops, and then you can see that the temperature now is decreasing continuously from here to here. Okay, and similarly it goes from 75 to 50 as it goes across here. So that's this method. So now it's come out. Once it has reached a steady value, it has come out here. Okay, I'm printing only one decimal point here, but the calculation actually keeps it at many decimal points. Okay, now this is a very simple program in which I use this method. Okay, this method of iterative thing. So this is called the method of over relaxation. So that is, it's a kind of relaxation scheme. That is, you have some boundary points specified, and then you start with some interior value, which is let's say put equal to 0. Okay, and then you let the whole system relax to its equilibrium value, such steady state value. Okay, so that's what it's done here. So every time you compute from using the equation, the derivative equation, using the derivatives, the new values which it can obtain there at that point. Okay, and continue that till all your second derivatives in this equation has vanished. Okay, that's a method of over relaxation. And I should warn you that not all elliptic partial differential equations can be solved using this. In some cases, for example, this may not go into this may get into a kind of unstable situation. In that cases, what you do is to use this equation to get the new value of uij. So let me call this as Sij here instead of uij. Okay, I call it Sij. Okay, and I say that my new uij is actually, I would say that my new uij values are my old uij values. So let me call this new as my old uij values, which is uij itself. Okay, times some number alpha plus 1 minus alpha times Sij. So I compute the new Sij values from my old values, okay, using this equation. but I don't use all of it as for the next uij values. I mix them with the old and the new, okay, with some parameter alpha. So in the limit where alpha goes to 0, it's this relaxation scheme, otherwise it's something slightly different, okay. So now, so in the limit alpha going to 0, it's called method of over relaxation, okay, where we are taking the new value as the one which is obtained from this equation straight away, okay. Or we could, in cases where that is unstable, where it is not going to a steady state, you could achieve better numerical result by mixing the old and the new value with some parameter alpha, and the alpha you tune according to your equation, okay, according to stability which you obtain, okay. Now that's called a method of relaxation, and then when alpha equal to 0, we call it a method of over relaxation. So now that's a case where we had the boundary conditions themselves were specified in terms of the u values at the boundary. Okay. So now, as I said, that this may not be always the case, okay. So you could instead say that I don't know what the boundary values are, okay, but I know what the derivatives are, okay. Now, so you can have this equation in two different forms. One is the derivative given at the boundary, or sometimes the value itself is given at the boundary. So value itself is given at the boundary, you can use this, okay, and then you have to solve only for the interior points. Now the value at the boundary is not given to you, okay, and then you have to also solve for the u values at the boundary, okay, and then we know that if you want to write, for example, this equation at the boundary here, and then you will have problem with terms like uj minus 1, uj minus 1 if I want to write here, because j is 0 here, so j minus 1 will be u minus 1. Okay, so in that case what we do is the following, that we could still use this equation, but what we do is we use the boundary condition themselves to specify the values at the u values at this points minus 1, etc. Okay, so that is, let's say if you are given del u by del x equal to 0 as the boundary condition at points I equal to 0, along the line I equal to 0, okay, and then I have the del u by del x I will replace by a difference equation, okay, and a symmetric difference equation, okay, and then I would say that that is u1j minus u minus 1j by 2 delta x at I equal to 0, and from this, since I know what derivative is, I can get the value of ui minus 1. So let me show you that here in this particular example. So as I said, now let's say we have a boundary condition on this line as given as del u by del x at x equal to 0, x equal to 0. Let's say that's a boundary condition given to us. Okay, so this derivative of u at this boundary is specified, or some value, some value c. Okay, it doesn't matter. Some value c is given to us. Okay, now that means we don't know what the u values here are. We have to solve for this. Now if I write the difference equation for this point, that is 0, 2. So if I write it for 0, 2, okay, in this equation, and then I have, remember my equation had the first point was ui plus 1j, so that is u1 2, and the second point was ui minus 1j, so allow u minus 1 2, okay, and then I had ui j plus 1, that is 0 3, and the next point was ui j minus 1, so that is 0 1, okay, and minus 4 u 0 2 equal to 0. That's my equation. So I could be using method of over relaxation, and I could write this as equal to 4 0 2, but then I don't know what this point is, right? So that's what, so if to solve for the u value at this point, okay, I need to know what u minus 1 2 is. Okay, so how do I get that? But I know that del u by del x at this point is 0. Okay, so what is del u by del x at this point? Okay, so I will write now del u by del x as u x, okay, so that is del ui by del x, I will write as ui plus 1j minus ui minus 1j divided by 2 delta x, whatever my delta x was. I can write it like that, okay. Okay, now this is called the symmetric equation for symmetric difference equation for the first derivative, okay, where it's symmetric about I, that I plus 1 and I minus 1 divided by 2 delta x. So I can use this equation here, okay. And then I can from this, for example, for I equal to 0, okay, I could, and this equal to c, right. So for I equal to 0, I will get this as 2 1 comma j minus 2 minus 1 comma j as c times 2 delta x. Okay. So from this I can obtain ui minus 1 j for all j values, and I can substitute that here. Okay. So that's one way of doing it, and I can do this for all boundary points. Okay. So now that's a derivative boundary condition. Okay. So we see that you can either use boundary points themselves has been specified. Okay. So it use it. Okay. Or you could use boundary conditions given by, so when you want to solve this equation, you could either get the boundary points themselves, the boundary points specified as boundary conditions, then you solve this equation only for a set of interior points, or else you have the derivatives specified at that case. Okay, so if the boundary values are specified, then you solve only for the interior points, okay, and you could use relaxation methods or you could use matrix methods to solve this equation, to solve for the temperature inside. Now if the boundary is not specified and the boundary values of u are not specified, but its derivatives are specified, okay, and then you could use this equation, the difference equation for the derivative, to obtain these fictitious points which are outside this grid, okay, and then substitute them back into this equation. You could have even mixed boundaries, that is, you have derivatives specified at one point, okay, but the values specified at other points, okay, and then you would have to use a mixture of these two, and then you may have to solve for fictitious points, the boundary values here, using fictitious points beyond this, and but only interior points on this side, etc. Okay. So that's a simple method of solving an elliptic equation, in this particular example the Laplace's equation, okay, for using this relaxation methods. Okay, so now next what we will be looking at is the heat equation, that as an example for parabolic differential equation. So we will be, the next class we will be looking at equations of this form, that is when you want to look at what's the heat flow across a one-dimensional wire. Okay, so then we would have to solve equations of this form, and then how do we solve that equations is what we will be discussing in the next class.